Hello, my name is John Watson, and this is Southern New Hampshire's CS260 online meeting, and we are covering Lesson 5, which is hash tables and chaining. In this lesson, we're going to look at taking something like a structure like an array or a vector and be able to use it to very, very quickly access exactly what you're looking for, a specific piece of data that you're looking for. And the way in which we do that is something called a hashing algorithm. There are many kinds of algorithms. Probably the simplest one is using a modulus function. And so let's just take a moment and review the lab instructions. We've got our standard auction bid files for test data, and we've got a starter program which has got a menu structure to it. We're going to just be able to load the bids from these files, display them, find a bid, remove one if we want, and obviously exit. And we've gone a little bit further here by indicating what the public API for your hash table class should look like. Basically, you've got a constructor, a destructor, an insert method which takes a bid, which is a struct in C++, a print all, which is going to iterate through them, and a remove method, and our favorite, the search method. So let's take a quick look at the data set that we're going to be dealing with. And I'll show you an interesting trick if you didn't think of doing this. So this is the December sale, so it's a smaller file. It's about 180 bids in it. And the thing with a hashing algorithm is you need to look for a value that is relatively unique, that can uniquely identify a particular bid. So like if I wanted to look for this Canon EOS 7 camera, the obvious choice for what we have here would be this auction ID. So one of the fun things you can do, this is just a data file, so it's yours to play with. We could take this and insert a column, and let's call this our hash column, or hash value. And we're going to make it a formula, and we're going to have the formula be mod, which is the modulus operation. And the number we're going to take the modulus division from is the actual auction ID. And the divisor, and we're going to pick something, we said 180, let's just say, I don't know, let's just say 240. When I hit enter, it comes up with a value of 71. The key to a hashing is with arrays and vectors, the data structure is relatively fixed in size. And so one of the simplest ways to construct a hash is to use this modulus division operation, where the key to it, though, is to know how many buckets or items are the size of your structure. Now, I arbitrarily chose something and said 240 elements. Which is enough for the smaller one, but not enough for the biggest data set. So once we have this, we can go ahead and copy it here to the end. And the reason for doing that is kind of interesting, is it gives you a sense of what these look like, or what you might expect to find. The other thing that Excel offers you is a way to try some different formulas, because if you're doing calculations, instead of writing code, trying to figure out what it's doing, and repeating this over and over, you can use a tool like Excel or something else and do some calculations here. You can add some columns, you can analyze them to see which ones work better or worse. So in this case, we're just taking the auction ID, dividing it by the number of elements in the array or the vector, and then we're taking the remainder or the leftover portion. Now, like what often happens with hash tables is you have to account for the fact that you have what's called collisions, which are when two or more items become a, so let's see if I can do this. There you go. Two or more items collide or come up with the same value, and here's a good choice here. So the ice maker and the Samsung 40-inch television, they have different bid IDs, but their remainder ends up being the same. So there's a case where when we insert one of these, we're going to find there could be something already there, or we insert it the first time. When we try to insert a second one, there's another value there. And that leads us to another part of the hashing algorithm problem, which is how do you deal with these collisions? Two common approaches that the textbook covers are what's called chaining and linear probing. Chaining is where we have our table or a vector array of elements. And if there is a collision, instead of inserting just the data item, in this case a bid, what you do is you put it in a linked list. So if two different items hash to the same value, like we saw here, when we come to it, we would find actually a small, hopefully short linked list. And we might have to, make a step or two traversing in through the nodes to get to the actual item we're looking for in a search. And we'll see that implemented in a little while. And that leads to one of the real challenges of hashing is how to determine a good formula or method or algorithm for computing the hash. There are lots of them. Some of them are very compute or CPU intensive. So you have to weigh it against what makes sense. If it's just a quick little thing and there might be some collisions, but you just need to get it in there so you can pull things out very quickly, that might be sufficient. And in fact, the built-in framework libraries that you'll find in various programming languages like C++ or Java, C#, things like that, they actually have a lot of these structures built in. We're going to build one by hand so we can study and learn and understand what really makes up this structure. So now that we've got an idea of what we're going to do, let's go back to our assignment and our usual format here. We're going to, actually, let's go here. We're going to go in, and first thing we want to do is download our lab files to begin with. Same thing we do each week. We'll extract them here. See, I don't need this guy anymore. And once again, we have our parser routine for parsing the CSV files, and we've got a basic struct, or excuse me, a structure or skeleton for the program. So in Eclipse, we'll go ahead and create our usual new C++ project. We want to use the Hello World template because it's very simple to start working with. And we're going to call this something like Lab 5.2. Now, once it's built, remember, we need to next go in to the properties and set the minimum C++ language standard that we're going to follow. So we go to go to Properties Settings, C++ Build Settings, and under the tool, we select our compiler. We go to the miscellaneous and we add a space -std equals C++ 11. That's going to allow us to use C++ 2011 syntax and parameters. And notice as soon as I did that, these errors went away. And as before, now that we've got our empty structure built in our project, what we're going to do, and here's our new project, we're going to go in and there's a source file. So we're going to take and we're going to copy these guys over to here. We don't actually need this guy anymore, but I like to delete it in Eclipse so we can see that. Right now, there's nothing shown. So if I delete, actually, next thing I'm going to do is I'm going to do a refresh, right-click, choose refresh, and it picks up the additional files. And I'm going to take this and I'm going to delete it. And then we've prepared our workspace and our environment for the work we're going to do. As before, if we go back and look at the instructions, we need a structure to hold the bids. You can use either an array or a vector. So we have some code that we can borrow and use for that. So that's actually not that interesting. We need to initialize the structures, implement some logic to free up storage, calculating the hash value. That's going to be the interesting part. Implement logic to insert a bid. Be sure to check for key collisions using the chaining technique. And implement the logic to print, remove, and search. So let's go back to Eclipse. And of course, we've got our little task thing, so let's start by defining our structure. Let's begin with a struct, and we'll call it a node. And inside of that, we're going to keep a bid, which, by the way, is, I believe, we're defined right up here. So we're actually going to hold a bid inside our node. This is very much like previous lessons. And we're going to need a key value for our hash. So we'll start with key. And the reason I chose unsigned rather than just int was the fact that it just avoids a little annoying warning that you get because you can't have negative values for an index. So just go ahead and put it in that way. And not only do we have the bid and the key, but we have a node pointer to our next node. And that's how we're going to implement our chaining. And we're also going to need a structure, or excuse me, a constructor. So let's do a constructor as the name of the class or the struct, empty parentheses is our default. And we're going to say the key equals, and here's a little trick. We're going to use, you don't have to do this, but I like to have things initialized and clean and know that they're in a good state so that I can depend upon them. And this value, let's see, do we like this or not? Wait, it's warning me we haven't got next initialized yet. So we're going to set next to be our null pointer constant. And now it's happy. So uint max is a C++ expression which is the largest unsigned integer maximum value. And it's just a way that's totally random. We're never going to hit that in normal operations. This can be useful if you want to be able to, say, test a key to know if it's been used or not. So there's one simple thing. This is our default constructor. And now we're going to have a second constructor that takes a bid, because that makes our programming work when we're coming to use it a little bit easier. We'll just leave that there. We'll make it go away. Initialize with a bid. So again, it's going to be node, only now we're going to take a bid, and I'm going to call it a bid, not a bod. Here's another little C++ syntax trick. I'm going to put a colon there right after the definition, and I'm going to type in node. What this will do is invoke the default constructor before it starts loading this. So in effect, I've got one set of code that initializes a node when nothing is given to it, and then we go about storing our values. In this case, the bid that's inside the node is going to be assigned a bid, which was the parameter that was passed to us. And we can do the same syntax if we wanted to. Now, it's not necessary for the absolute minimum operation of this program, but I just wanted to be able to show some other techniques and some slight improvements that you might take with you. So since we're taking a constructor with a bid, let's have one with a bid and a key. So we'll take the node, and we're going to have our bid again. And we're going to have a second one, which is key. And we can follow our same logic. We can call the other constructor, this time giving it just a bid. And then all we have to do here is say key equals a key. So following this through, if I were to create a struct and pass it two parameters, a bid and a key, before it actually starts executing the code inside this constructor, it's going to call the other constructor with just a bid. Same rules apply. This constructor is going to call the base one, which is a default constructor, initialize these values to make sure the state of our node is very clean and in a well-defined, well-known state. And then it'll come back to here and assign the bid, and then it will come back here to this constructor and lastly add the key to it. So this gives us just a little bit of kind of syntactic sugar, I guess sometimes people call it, our little syntactic tricks to make our code clean and concise, and yet also well written in the fact that you're only doing things in one place. So if we, for example, decided we wanted to change the key to initialize it to, I don't know, 0, right? All I have to do is change this one line. I could even say -1, which is bad because it shouldn't be a negative number. In fact, this will throw a compiler error when I save it. But let's just say I wanted to do 0. I can make this one change here, and the entire body of code is going to function normally. If I just simply copy and paste it, then I got to make sure I change them in all the places and make sure that we don't make mistakes or forget something. So that's a good habit to get into. Next, I believe we need a structure to hold the bids, and we're going to reach back to our friendly little vector, and this vector is going to hold nodes, very much like our linked list did, and we'll call it nodes. And one thing we want to do too is be able to manage the size, and this is another case of let's call it our hash table size. We'll say table size. And I think did I do this? We actually have a default size. The default size happens to be 179, which is probably not that good. Why don't we make this, we said 240. No, let's leave it. Let's leave it. I don't want to get fancy. Table size is going to allow us to change the size, as we'll see in a minute. And there we go. And from that, we can add, we'll come back to that in a minute. So now that we've got this built, let's see, one of the next things we have to do, where I can look here. This one? Nope. This one. Initialize the structures, implement logic to free storage. Let's find our structure, destructure here. I could have just clicked it and gone there. So we have our node list. In order to free storage, we can call the erase function. Let's see. We'll go look at a vector. And we'll look at some of its member functions. One of them is empty size, erase, erases elements. So let's take a look at that. Remove specified elements from the container. And there's a number of ways to call it. You can pass it an iterator. And what it's going to do is basically loop through and start removing stuff. And here's a little cheat line if we just call erase with the begin method. So I'm going to copy this and paste it into here. Only instead of C, it's going to be our structure is called nodes. And there we go. We now have that done. Can you check this? Yep. How are we going to calculate a hash value? Not that hard. We just need to use our modulus operation. Let's see. We're going to do. We need to return an unsigned integer, so we're going to do a return key, which is the value that we're going to pass into, which is the key value from this guy over here, our auction ID. When we call the hash function, giving it the key, we're going to take that key and we're going to use modulo division. So where's my modulo division? And we could use default size, but I'm going to instead use table size. And the reason I do that is because if we change the size of the table, we want to be able to use that new value. And then we get to our insert, which is really where all the fun begins. So the first thing we want to do if you're going to insert a new bid, which we're passing here, we need to create a key. So we're going to say unsigned key equals, we call the hash method. And we're going to give it, and this one gets a little bit tricky because our bid, we see the struct here? Now we'll just go to the top. The bid is reading data as a string. So we need to take that bid ID and convert it to a string. And we actually have that, I believe, in the printing. We had it in one of the earlier classes, or earlier lessons, I thought. Anyways, we'll just go ahead and do it like this. Semicolon there so we don't forget. So we're going to start with bid dot bid ID. Now that's actually a full-blown C++ string object. We want just a simple string of characters. And for that we can use the cstring function, which returns it as a plain old C-style string. So this will take the bid, access the bid ID, which is a string object in C++, and then we're going to use the cstring method to get back just to, let me see that, returns a pointer to null terminated contents. So this basically is going to give us back our string. But we got an error here because we need to pass it an integer. Because the way we wrote the hash function, which we need to, actually we should probably make that unsigned, but that's okay. And we have our a2i function, which is a method that converts an ASCII string to an integer. And we have something complete. So when we're going to insert a bid, the first thing we want to do is create the key. So we're going to call our hash function right here. And this is just, if we unpack it, like I said, you start out, we want to get the bid ID. We need it to be a string. So that right there makes it a plain old C-style string. And then we can use the built-in function that takes the ASCII string and turns it into an integer. Now we've got a hash, an insert or a key for our insert. Now one of the things you want to do, because of here, no. When we're looking at this, is we got to first look for the item and make sure there isn't one already there, because if there is one there, we have to add it to the node list, and that's what you're seeing here in this example. I'm thinking there was another one. That common hash functions. That's okay, I'll just walk through it anyways. So we're going to call, and this one gets a little syntax heavy. We're going to look for the old node. And the way you do that is you start with the nodes at function and you give it the key, which is the index into the vector. So the key is the key value that we just calculated. But before we do that, what we really want is the address, because this is a pointer. So I don't want the value of the node at that key position. I want the address of that because I need a node pointer so I can use to figure out if I need to add more to it. So we have to wrap this with the ampersand, which is the address of operator, and that will give you your address of the node as a pointer. Now we can start putting some logic in place. If no entry found for this key, that's going to be an if statement. I'll say old node equals null pointer. And I'm just going to have, before I start filling it in, we have an else condition. In this case, the else is going to be node was found. And we'll expand on that in a minute. If we do find a node, oops, back here. If we do find a node in that position, then we want to be able to add to it. The way to do that is to say, if no entry was found, then we'll just do a new node pointer. We'll say new node to keep things clear, equals new node. Now we're calling, oops, now we're calling the constructor. And if I hit control space, you can see our different constructors. I can say new node with nothing, it'll be empty. I can say new node with a bid, or new node with a bid and a key, which is the one that I want to use. And so we'll say bid, which is what we were given to insert, key. And there we have, we've constructed a node using the bid and the key. And at this point, we can just call good old nodes insert. Because we have a vector here, we're going to say insert a node. And this one's a little tricky. It would be easier with an array, but I wanted to do it with a vector just to show you what can be done. We're going to start at the beginning of the nodes, add to it the key, offset the number there, and our insert method takes there we go, the address of for the value type. That's what we're looking for. So we want to be able to give it the pointer of our new node. Save it, and we still have a problem. Here we go. So when we call insert with a bid, we calculate the key using the hashing algorithm, which is just for now a simple modulo division. And then we construct a node using the bid and the new key we calculated, and we insert it into the vector, beginning with this position plus the offset. If the key is 18, then it'll be 18 elements in. And then we pass here, we're passing the address of the node that we just constructed. Now, handling the other condition, if the node was found, we've got one of two things that could happen. Either there are no more entries or not. So let's take the case of if there are no more entries. So that old node that we tried to retrieve, that said if it was a null pointer, else it's not a null pointer. What we want to do is find out if that old node's key equals, and what's our magic value? Uint max, because remember we initialized them that way. up here in the constructor. When we construct a node, we set the key to a special value that we know about that wouldn't be used. If it's not, so this old node is not anything, then we can go ahead and we can say old node key, oops, I forgot this, key equals the key value that we just calculated. Old node bid equals the bid that we just created. And even though it may be said it's not a bad practice to make darn sure that our pointer is null, because we're going to rely on these values. So this is where some safe programming and some discipline and not just typing the least amount of things that will work. So that's what happens if the node was found and the key for that node entry happens to be uint max, meaning it's not been used. We assign the key, assign the bid, initialize the next pointer to null because that means there are no more nodes pointed to, and we're done. Otherwise, that means we have a case where there is a node and it has at least one value, because if the key is not uint max, it's a node that's not brand new uninitialized. Instead, it has a value, in which case we have to do the old walk the chain trick. And the simplest way to do that is with a while loop. I'll say old node next is not equal to null pointer, because remember that's how we walk our chains. Just keep iterating through. And we say old node. So here we're just going to reuse this. We got to the first node in the vector, and if it turns out that that next is not null, then we're going to just repoint that to the next one. Old, actually, I'll just type it. Old node next. So what this while loop is going to do is when we get to that first old node, if the next is not null, we're going to take and make the node be the next one. And we're going to keep looping through until we get to the point where it is null, in which case we've reached the end. And at that point, we just need to make that old node point to our new node that we're adding on the end. And we say old node next is going to equal, we'll create a new instance of a node, giving the bid and the key. So there we have it. Just review and reiterate. We're going to insert a new bid. We're going to calculate a key for our node using our algorithm, which we have right up there. Go look and see if there is a node at that point, or at that position, that key position. If there's not a node, if it's null, we simply create a new instance of a node and insert it into the vector. Else, a node was found. So then the next thing we do is we look at that node that we found and see if it's been used. This is, again, just safe programming. If it has been used, if it has not been used, then we just simply assign the key, the bid, initialize the null pointer, and we're done, because that node is already in the vector. Otherwise, if the key is not uint max, that means that the value of that node exists, and we start to do the chaining part of the operation, where we just use a simple while loop to walk through each one of these until the next pointer is null, and then all we do is create a new node instance and assign it to the next pointer. It's really that simple. Let's see where we're at here. Get too far off track. Oh, I keep forgetting I can do this. Printing all bids becomes really very easy at this point. We could do this by hand. let's come back to that one. That's not one as fun. That's a void. That's a void. So we don't have to actually fill those in yet because that will still compile. Let's stop and take a minute and see what we've got here. We've got our load routine. We've seen that. Yeah. So here we've got a case for we can pass in the first argument, which is the path, and actually a second argument, which is the bid that we want to find. And we right now have it defaulting to 98109. If we, and I probably shouldn't call it bid key. Might be worth showing a little trick if you haven't seen this. So key means something in this program, so that wasn't really a great choice. Let's use something, and this is a technique that all the important IDs have. It's called refactoring. We're going to rename. So if you select a variable anywhere, it could be here, or I could be down here and say, I want to change that. I can right-click, go to refactor, and say rename, and it opens up, and it goes into mode, and these are highlighted. So it's found all the references to this, and I'm going to call it search value. That seems to be, and then when I hit enter, oops, I wonder why that happened. Oh, there's a bug or something. Yeah, well, we'll just fix it. And so what that does is let it rename so we don't use the word key to mean something else that we don't really like. We've got our usual, we got a bid table, which is our hash. We got our clock for managing and counting things. And pretty sure that the last part of this is pretty straightforward. I think we actually had this fairly filled out for you. So case 1 is a load, which is not interesting anymore. Case 2 calls print all. Case 3, we grab the current clock, call a search. Is that right? Search 3? Find. And 4 is remove. Did we implement search? That one we're going to need. So let's go back and look at search. To do this, we're going to have to borrow some things. In order to search for something, we're going to need to, and we're going to give it a bid ID to search for. That's the design, although you could change and improve on that. First off, we need to find a key. So let's be good lazy programmers and just borrow this line. Maybe if I collapse this and this and this and this and this, almost make it. So here we've got a key, which we're going to find out. And next thing we're going to do is just see if we can come up with I'll do it this way. And I think we'll call this node instead of, it's not old node, just a plain old node. So we're kind of in the same boat as before. We're going to see if we can find it. If we return it, then we need to go. Now remember that with a hash table, oops, with a hash table, if the key was 7, then it may or may not be this entry or maybe one beside it. So we need to kind of look a little further. But we're going to take that key and let's see, we're going to say try and retrieve no using key. Matches key. We'll say if node is not null pointer. So that means we did get something back. and we use the double ampersand to indicate a Boolean AND operation. We say node key is not uint max, and, so I didn't mean to do that. Silly keyboard mapping. And the node that we found, its bid.bidid. We're going to call, because this is a string, we can call compare on it. And we're going to compare it to the bid ID that we were passed in up here. And if that compare operation equals 0, then it is a match. And that completes our condition for the if. So, given a bid ID, whoops, that was a whoopsie. I should have get for copying. Take that bid ID, grab the C string, convert it to an integer, call the hash method. Now I've got a key, which is an index into the vector. And now we're going to use the node's at function to get that field, or that element rather, and we're going to return the address as a pointer. So now we've got this node. We want to make sure it's not a null pointer, that we did actually get something back. And we also want to make sure that it's not a new initialized unused node, just in case. And if that node's bid ID compares or is equal to the one that we were passed in, then we know we found it. And at that case, it's really a very simple. Now, the search function is going to return the bid you're looking for, so we just need to return node bid. And that's how simple a search is. You just calculate the key, and then the rest of it is really just noise about managing and manipulating a hash table with nodes and pointers. And then, of course, we get to the case where it's not. And you could reverse this, I guess, but we could probably. We could actually probably do this. Why don't we change this around? Put this up here. We'll copy this just to save us a little bit of typing. And I want to be more precise. I'm going to return the empty bid that we left hanging around up there, just in case you might have needed it. So this might make it a little simpler. Try and retrieve it. If it's not a null pointer, actually we could say if it is a null pointer. That wasn't that, because I didn't save much from that. If the node is a null pointer, and the OR is a shift vertical bar, or the key equals uint max, return an empty bit, because that's been initialized to nothing. So that might just seem a little cleaner to you. Calculate the key, look for it. If the node is empty, or it's initialized, if there's no node, or if the node was empty because it's been initialized to uint max, then we return the bid, the empty bid. If it was found, we return that node's bid that was returned to us. And then the last case is our good old chaining. Excuse me. This is going to be a while. That's not very interesting. So we already got a node here. So while node is not equal to null pointer, we're going to say if node key is not uint max, and node bid ID dot compare And the comparison is going to be to the bit ID we were given. If that compare equals 0, that's a match. Then we return that node's bid. Yeah. Now that's the if condition. If it's not the case, that it's going to fall through, and we're going to say node equals node next. And that simple little, oops, what did I do here? Oh, I was doing dots, wrong language. As long as it's not null, we're going to make sure that this key is not empty. And if it matches, we return it. Otherwise, we're going to go for the next node, come back around, and repeat the operation until we find it. We get to the end, and it falls out of the while loop, but we haven't returned a matching node, then we're going to return an empty bit. So let's take a shot and compile this and see what we come up with. It reminds me, I always forget this. Now that we've compiled it, I'm going to be lazy and copy our two files into the debug directory. So we have it. And we had a good compile. We've got an executable. I'm going to copy the path. Save my, oops. That wasn't very good. Copy. I'm going to open a PowerShell prompt. Change to the D drive, CD, oops. Go to here, there we go. And I can just do lab, press the tab key, and up it comes. We say load bids. Ooh, got an error. That's twice. I got one last week too. Ah, size. Probably got for running too quick. I was focusing on the main methods. Initialize the structure. The hash table has nodes, so I'm going to say nodes. Size. And we're going to use table size. And the reason I did that, and this is where we could possibly improve the operation, is, oops, we could even get fancier and add a second constructor like so. We could say hash table just like we did with the nodes. And we could say I have a tendency to get my G's and N's mixed up. In this case, what we want to do first is save the table size and say this, which is table size equals size. And so see, now I can, oh, that should be right. You just need to compile it. I can't do the call a constructor because this one is set to resize it based on the table size, so I'll just do it this way. I need to compile it to find it. What did I do wrong? Ah, spelling. There we go. That was a pretty fast load. Let's just go for broken call find. Whirlpool washer 98109. What did our main method look like? First argument was that. Second argument was a search value. So let's find something interesting. Let's take this guy, 97951. For that, what we'll do is we'll say copy this. Anything to save typing a few letters. Paste. And what is that? 97951. Load them. Find it. And there's 97951. Now let's pick something that's a duplicate. We'll take this guy, for example, 98190. And what's the difference? We should get, hopefully, the Office Electronics rather than the weight bar. Load it, find it, and we got the Office Electronics. So there we have it. The printing is somewhat mildly interesting, but it's really, we've got all the guts. I won't actually go over that because we've got all the guts for that. We've got the ability to iterate through the list. Starting at the beginning and finding all the nodes, or not finding them, but walking down the list of nodes. Removing this really just the erase, which we had ready. The other thing is with the key. We could implement that in a second. Let's see. Now, don't hate me for this. Get a key. So we'll hash the bit into a key. Put it there. Then change that to erase. And I just implemented move. The way that works is you get a key, call a hash function to get the key, and then you erase it. And your offset is the beginning of the nodes plus the key index. So are there any questions?
I don't have any questions. Most of what you went over answered the questions that I had. Most specifically in the insert method, I was having some trouble there, but now that I see kind of what I was doing wrong,
yeah, so
it makes sense.
Everyone's different. Like I said, I'm a visual learner, so I have to almost see these or sketch them out on paper. So if I understand it, then I can kind of turn it into code.
Right.
Anything else?
I don't think so. That answered all of the questions that I have. It's good to see you do it because then it kind of makes a little bit more sense. I kind of have to talk it out too. So hearing you kind of talk through it, that's kind of how I learn. So, so that was
Come
helpful.
On.
Yeah.
You got a little smile when the first time I ran it, it crashed.
No.
It happens to all of us.
Yeah. Oh, yeah, for sure.
You forget things.
Sure. Yeah. It does make you feel better. Like, oh, maybe I'm not so ridiculous. But yeah. No, that was very helpful. Thank you.
Good. I was hoping that was something easy and I didn't have to go dig into the debugger again.
Right.
But that's always a tool there if we need it.
Yeah.
Any questions on this week's assignment?
None so far. Making some progress, so I can't think of any.
The biggest takeaway, I think, for biggest takeaway, I think, for this course is just to understand two things: the concept of algorithms and being able to
Right.
put something together. And that's why earlier courses we stressed pseudocode so much, because you really got to think through the problem. You can't just start
Right.
coding. And then the data structures, that the fact that they're paired together, there are different structures. You could do everything with an array if you wanted to. And early days of programming, that was all we had, and so you did everything with an array. But as time went on and as computer science improved and as the technology improved, we got some more advanced tools in our libraries and techniques for doing stuff. And so being able to choose the right one is, I guess, a key thing. To be honest with you, this is really kind of an academic exercise. It's not that often that you handcraft things like this
Right.
in a professional job anymore. But what I think is super important is to understand what's going on. Not so much that you're going to need to do all these by hand, but that you know what they are, what they're for. You know what a linked list is all about. You know what a hash table is, or some languages call it a hash map. So being able to find a reference and have some sense of what it is and what it's about is, I think, a concept that you need to kind of take with you. It's having your toolbox.
Right. Right.
Did you happen to think of the trick of using Excel?
No, I hadn't. So that was really cool to see.
And the nice thing is, two ways. I think I touched on it briefly. The way in which this thing is put together is, if I wanted to try measuring the performance of something else, I could, here's my hash here. There it is. Everything is using the hash method. So I could just do it by here. If I read an article, if I did a search and found something and said, oh, you could do it this way better, it's relatively easy to change the algorithm and see the effect right away. By the same token, you could even play with some things here. We just did use a simple built-in function, but if it's math, it's doing the calculation, and I don't even know what all the function libraries are. It's a whole bunch: average, count, min, max. But you could calculate them and do them in here. You can see what the effect is.
Yeah, that's definitely a good tool.
I didn't actually show it, but I guess I'll leave that exercise up to you. Because I put the table size and added the second constructor, for the hash, we could easily go to the main method and add another parameter, or even prompt if you wanted to, but to pass in the table size. So this is optimized for the large one. That's actually kind of an interesting question. What if we did this and we took, I don't care about that, but if we took this off, what would happen? It was taking essentially 0 seconds to load. Took a little more. Right. Now, what you'd find here, what would the effect of this be? What would you expect to happen? The technical term for that is there's a buttload of chaining going on.
Oh, I see.
Right, because we initialized it. What was the default size? Default size was 179.
179, yeah.
So every modular division is we have to fit this in 179 buckets. And our main file is 18,000 bids. So that's a lot of chaining.
Right.
But like I said, if we could either make it a parameter to pass in, or you don't have to get that fancy. You could just change that to 18,000 if you wanted to.
Mm-hmm.
Just out of curiosity, what if we did that? Run it again. Only now with 18,000. What did it take last time? 671.
Mm-hmm.
Ooh, slightly faster.
Huh.
So without analyzing it, I probably would guess that that's because it had less to do with the walking the nodes, because there weren't as many collisions.
Right. That makes sense.
Or, well, this is net. Well, You said 179. Let's see what that does to change it. Oh, I had to do it here. Let's just, for arguments, I did that. We'll copy that down to the bottom. Get rid of that guy. And we'll resort this. You'd have to count the duplicates to see if there was more or less. I'm just kind of visually skimming it. Usually at most it seems like there might be 2. But again, that's where, having this algorithm, all you got to do is, in this case, change the size.
Right.
Or if you want to try a new formula, you change the hash method. And you've got it. All right, anything else?
I don't believe so.
Good. All right, well, thank you.
Thank you, sir.
Welcome.
Have a good night.
You too.